Okay, so electricity outcome number 3 notes. So we're looking at electricity in the home, and so here it basically shows you from one end to the other. And so you have a power generating station where a magnet is spinning through a coil. Maybe they're burning coal, maybe they're doing it through hydroelectricity, maybe they're doing a solar farm, maybe they're doing a windmill, whatever the case may be, they generate electricity. Now, that needs to be stepped up because electricity, there's a lot of resistance in this long length of wire from there to the home. So if you increase the voltage significantly, you can actually reduce the effects of the resistance. So they bump up the voltage to 500,000 volts, goes along the power lines. I mean, you've seen these along the highway as you drive a lot from here to Calgary. Comes into an area, drops down to a substation. You've seen these. They're usually fenced off, and it says warning, high voltage, and then it goes along the power lines. In the old days, up top. Nowadays, they tend to be more underground, but the voltage is now has been dropped down to around 60,000 to 138,000 volts, and then it gets to a distribution station. You see these in town; they're all fenced off, and then from there, the wiring usually goes underground. It still goes to a step-down transformer, brings it from 25,000 volts right down to 120, 240, and then that goes in the home for use. And we use alternating current in our homes, right? DC is mainly for batteries, a little bit for small engine generator, but for our homes, they're all AC powered, and 120 volts is the standard for North America. And we use transformers to step up or step down the voltage when it's required. Okay, and so it goes from the grid into your home. Okay, and it enters through a step down transformer, and then it goes to this power meter that's mounted outside your home. Now, they used to be like this big glass bubble, and you could see the little aluminum wheel turn, and you could see the numbers tick off, and it monitors how much electricity is used, and then they charge you based on that. Now it's electronic, and so you don't even see this anymore. It's just kind of I think it's a black. I guess it depends. It's a blackish looking box where this once used to be. After it's metered, it goes into the service panel, and there's two live wires that come in. There's a hot wire and a neutral black wire, and there's a green wire that's your ground as well. And the black wire carries high energy electricity. The white wire returns low energy electricity back to the panel. The green ground wire allows the current to go back to the earth. Don't spend any time trying to memorize the colors. I'm not going to tell you it's not important. It is. However, not for Science 9. Okay. Modern homes have circuit breakers, and the breaker acts like a switch. So if there's too much current going through, the bimetallic strip will bend and open up the circuit. The current stops flowing until the circuit's reset. You don't want too much electricity flowing through a wire because wires are only rated for a certain amount of amps, and if it gets to be too much electricity going through, the wire gets really hot and can cause a fire. We call that an electrical fire. Older houses have a fuse box, and in the fuse box there is a little fuse. The base of it is like a light bulb, and then there's a glass top, and there is a little piece of wire inside. If too much electricity flows through, the wire gets hot, and it has a melting point that's set at how much amperage is going through the circuit. Okay, and so that little piece melts, and then it breaks open the circuit, so then the house doesn't catch on fire. Now, in order to fix this, you actually have to buy a new fuse, and they're not expensive. I think they're like a couple of dollars each, and then put them in. Whereas the circuit breaker, there's a spring-loaded switch. You can just reset it that way. Okay, we still use fuses today. Some vintage homes still have the fuse box, but that's in the top of your electric stove. There's those fuses there, and in automotive electrical system, there's fuses there as well. Here's what the top of it looks like, and there is your typical circuit breaker that's in your service panel that's in your basement, usually close to the furnace, but not always. The lower part of the service panel has additional spots so that you could actually add more circuits if you need to. Okay, and so we went away from the fuses because once they're done you had to replace them to these ones where you could just simply reset them. Now from time to time these could actually fail. I had one fail at my parents' place, so the dryer kept going off because the breaker kept breaking open. Uh, and then it turns out the reason it was doing that is the wire in the circuit breaker panel had somehow worked its way loose over 40 years. And then uh, my electrician who came in quickly just popped it out, tightened it back up, closed back up, and haven't had any problems since. Uh, I'm nervous to open up anything like this because of possible shock hazard. Plus, you would want a certified electrician doing work. Uh, Nothing worse than burning down your own house because you did a patch job. Home wiring. In order to install or modify wiring in your home, it's necessary to get a permit from your government. You got to be careful with this. If you build your own basement but you don't get the inspections done and it's not certified, if there was a fire, your insurance company could possibly say that, I'm sorry, this was caused by negligence. We are not going to cover that. And so here you can see the outlets are all in parallel. There's different branch circuits, and each one has its own circuit breaker and a main circuit breaker for the whole house as well. Digital devices, I feel like I've already covered this, but I'll cover it again. So in digital devices, it's the same four basic circuit elements present: conductor, load, source, control. But the wires are thinner and they have way more connections in them. The loads are resistor lamps and motors. Switches, there's millions of switches. These are called transistors. And the source of electricity is a 120 volt electrical outlet, or it could be a battery. And there's the two conditions: on or off, open or closed, if you will. And so that's binary code machine language. Electronic switches in modern devices are transistors, and there's solid state components that can be turned on and off by electrical signals, and there is the symbols for them. Okay, which brings us to mathematical work. So measuring electric power. So power is defined as energy per unit time. And so here is the energy power time formula. Uh, Electric power describes the amount of energy converted into other energy like heat, light, motion, etc. It's per second. How much energy is changed per second? So the unit will be joule per second. Here's the power formula. It's energy divided by time. And you, of course, know how to manipulate this from your math class. And if not, here is the EPT circle. And if you want an E formula, you cover up E, it's P times T. If you want a power formula, cover up power, it's energy divided by time. If you want a time formula, cover up time, and it's energy divided by P. You have to use the base units. So for power, it's watt, energy is a joule, time is the second. Okay, and there's also another formula with power that has I and V in it. Okay, so power is equal to current times voltage. Okay, and then if you want a P formula, you cover up P, then it's I times V. If you want an I formula, cover up I, it's P divided by V. If you want a V formula, cover up V, it's P divided by I. So here you go, problem 13.6 amps going through an electric baseboard, connect to 110 volt wall outlet. What is the power? So it's going to be equal to, I don't know if I can do this very well here. Power equals, so you have to write down what you have. You have I and V, so find P, so power is equal to I times V. Power equals 13.6 amps multiplied by 110 volts. Power equals, I think it's 1,496 watts. Okay. And next one, here we go, 100 watt light bulb used in a 120 volt socket. Calculate current this time. So I need an I formula. So there it is. I equals P divided by V. 100 divided by 120, and 0.3 amps is the answer. Okay, so there's some more practice for you to try. Find the power that runs on 10 and 120. So you're going power equals I times V. Power equals 10 times 120. Power equals 1,200 watts. Next question says a 1500 watt dryer runs for 200 seconds. Calculate the energy used. So energy equals power times time. Energy equals 1500 times 200. Energy equals 300,000 joules. Then here's one. I equals P divided by V. That's equal to 900 divided by 120. And that's equal to 900 divided by 120 as amps.
You're killing me, dude.
So sorry, I'm still online here. So,
No,
and then we have the next one: flashlight with 2-volt, 1.5 volt cells ends up with 3 volts, and current is 0.5 amps. Calculate power. So once again, power equals IV. Whoa, IV 3 times 0.5. And that gives me equal to, sorry, I can't write very well. This case, 3 times 0.5 will be 1.5 watts. And then there are a set of questions you're going to do. I'm going to stop right there so that you can work on that if it'll let me.